Hey, hey guys. Big apologies. If you can't tell or you don't know, it's pretty late right now, so this one's also gonna be a short one, kind of like yesterday, but you're gonna have to excuse me. I had a lot of work to do during the day, and then also on top of that, yeah, I got a lot to do these coming few days. I'm gonna be moving into school and whatnot. So hopefully I can kind of try and do something. Tomorrow is probably going to be the hardest day. But I actually can't tell because it's not going to get much easier. But I have a flight the day after tomorrow, early in the morning. So there's going to be packing and a lot of stuff like that. But we'll see. But I don't want to delay this one too much, so let's get straight into it. So for IBM, I think we've done all of these, or let's see, which ones have we done? So gray code was weird. I don't think I did it. Yeah, I didn't do gray code, but we did find smallest divide. Rotate image, I feel like I've done rotate image. Yeah, rotate image. And then let's go to the home page. Is today an easy? I doubt it. You usually don't get 2 easies in a row. Oh. How long am I gonna get stuck on this easy? Can you guys remember yesterday? Also, yesterday we had our first viewer. What was his name? I forget his name. But if he comes back, I'll try and check it more often. Maximum length substring with 2 occurrences. Given a string s, return the maximum length of a substring such that it contains at most 2 occurrences of each character. At most 2 occurrences of each character. I mean, do I just maintain a frequency counter? Like, I mean, I guess I'm just gonna do that. Let's go for I char in enumerate s. We'll do freak char equals freak dot get char 0 plus 1, and then while freak dot values. Wait, we'll do while max of freak dot values is greater than 2. Oh, we need to have an L. L plus equals 1. I said L minus equals 1 if freak for S at L is less than or equal to 0. It'll delete it. I mean, I don't really know. We could just hold it. Okay, it doesn't matter. Oh, it doesn't matter. Should we just do a default dict? I mean, I don't care. Freak S at L. L plus equals 1. Longest is the max between longest and that. And we're gonna return the longest. This should work. Oopsies. This should work. Oopsies. This should work. Okay. Okay. What are people doing that's so fast? Yeah, so default dictionary makes sense. Alright, whatever, I got distracted. Before I get distracted again, let's check my whatever. 800, I think we're gonna get past. I think we're gonna make top 700 today. Or tonight, hopefully. Alright. What was I gonna do? We have gray code. Like, what is gray code? I forget, it was something. It was basically let's see. O2N. What's the size? One-line solution. Are you kidding me right now? I mean, this seems like intense. I mean, I don't even know. Why did this get recommended to me? Who did this? Was this you? No, this must have been you. No, it wasn't you, so it must have been. Oh, I'm stupid, it was right here. This is tough. Math backtracking. I can't do that. Why is this a medium? I need to learn how to do backtracking. Should we do some backtracking, guys? Let's do some backtracking. LeetCode. Backtracking. So backtracking is after priority queue. The first backtracking problem is medium. That's how you know it's bad. Same with tries. Graphs as well. Number of islands. Oh. Max area of an island. And rotting oranges. I want to do rotting oranges. What is the difference between a try and a prefix tree? Aren't they the same? That's what I remember. It's the same. Given an array nums of unique integers, return all possible subsets of nums. I don't even know. Let's watch this guy's.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem subsets. So we are given an integer array nums, and all we need to do is return every single possible subset that we could create from the input nums. And we do not want to include any duplicate subsets. So what is a subset? Well, let's say we have 1, 2, 3 as our input. This counts as a duplicate, we're not going to include it. And 3 is another subset, 1, 3, 2, 3, 1, 2, 3. The original input is technically also a subset. And we also don't want to forget the empty subset. So no matter what we're given, an empty subset is technically a subset of this as well. So if we want to create all the subsets from this input, we have a choice for every single element. So for this 1, we have a choice of include the 1 in our subset or not include the 1, so we get an empty subset, right? So we have that choice, and we have that choice for every single input element. So in total, we have 2 choices here, 2 choices here, and 2 choices here. So this is going to be 8, or in other words, 2 to the power of n, where n is the size of our input, right? So this is the number of subsets, and we don't want the number of subsets, we actually want the subsets themselves. So how long could a subset be, right? Well, we could have a subset 1, 2, 3, right, the size of our input. We could also have subsets that are smaller, right, like 1, 2, maybe 2, 3. So as you can tell, this is not going to be an efficient problem to solve. We have this many subsets, and each subset could be up to length n. So the worst case time complexity of this problem is going to be n times 2 to the n, regardless of how efficient we make it. Because given the constraints of this problem, we don't want the number of subsets, we want the subsets themselves. We have to make it inefficient. So with this in mind, we can just jump straight into backtracking, which is the brute force way of solving this problem, but it's also pretty much the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first, we can choose to add 1 or not add 1.
Nums can be 10. So what is 2 to the power of 10? 1024. Times 10. It's just 10 to the power of what? 2, 3, 4. Oh, that's not bad at all. Okay, where were we?
One, and that will give us 2 subsets, one subset with just 1 and 1 3. forced way of solving this problem, but it's also pretty much the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first, we can choose to add one or not add one, and that will give us two subsets, one subset with just one and one empty subset. So along this path, we can decide now, do we want to add to or not add to? So with one decision, we will add to, and the other decision, we won't add to. So we'll get 1, 2 as one subset, and the other subset will just be 1 by itself. And we can actually repeat that on the right subtree the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first, we can choose to add one or not add one, and that will give us two subsets, one subset with just one and one empty subset. So along this path, we can decide now, do we want to add to or not add to? So with one decision, we will add to, and the other decision, we won't add to. So we'll get 1, 2 as one subset, and the other subset will just be 1 by itself. And we can actually repeat that on the right subtree for 2. So we can decide to add 2 to this empty subset, or we can decide to not add 2 to the empty subset, in which case we'll get a subset with 2 by itself, or we'll get the empty subset again, right? This is where we're just not adding anything. And lastly, we can decide whether we want to add this 3 or not. So if we add the 3 to this subset, we'll get 1, 2, 3. If we don't add the 3, then we will remain as 1, 2. And we can repeat that decision over here. And that's basically what I'm going to do now, right? Repeat that decision for every single one of our, like you can call them nodes or you can call them leaf nodes. That's just what we're doing. So if I add the 3 here, we'll have a 1, 3. If I do not add the 3 here, we'll have the 1 by itself. So you can kind of see these are 4 unique subsets, right? Now let's build the rest of the 4 from over here. So I have the choice, do I add 3 or do I not add 3 to this subset? If I do, I will get 2, 3. If I don't, I will have 2 by itself. And you can see these two subsets are different from the subsets over here. These are still unique. And lastly, we can choose to add 3 to the empty subset, or we can choose not to add 3 to the empty subset, in which case we'll get a single empty subset. Now you can see we keep multiplying by 2, right? So here we had 1. We multiply by 2. Now we have 2 subsets over here, right? We go down and let me show you. Multiply by 2. Now we have 4 subsets over here, right? Then we go down one more time, multiply by 2, we have 8 subsets, and they're all unique. This is our result. This is what we're building in this problem. This is backtracking. Now, if you want to know how to do this backtracking solution in code, let me show you right now. So let's do this with backtracking. So we're going to have a result list, which we're going to add these subsets to. And I'm going to do this with backtracking depth first search. And I'm going to write this function inside of this function so that we don't have to pass in this variable or this variable into it. We'll just have access to it by default. But I'm going to pass in I, which is the index of the value that we are making the decision on. So, we had 1, 2, 3. So initially I'm going to pass in index 0 for this one. And, this will be index 1, this will be index 2. That's going to tell us whether we decide to add 3 or not add 3. So this I will tell us which element we're currently visiting. And so we know that the base case for this will be if I happens to be out of bounds. So if it's greater than or equal to the length of our input, we know we're out of bounds. And in that case, we can just return. Now, what data structure am I going to use to build each subset? I'm going to have an array, and I'm going to allocate it outside outside of the function so that we have global access to it inside of this function, right? So let's say let's actually call it subset. Let's say that it has the subset that we currently have. If we ever reach the base case, we know we've gotten past our leaf node. So what we can do is add that to our result. And I'm also going to add a copy of the subset because the way it works in Python and in most languages, this subset is going to be modified, right? So we know we have two decisions. So this is the decision to include nums of I. So this is like our left decision that I showed you in the picture, right? So what I'm going to do is to the subset, I'm going to append nums of I. And then I'm going to recursively run depth first search on the next element, so I plus 1. So this is going to be like the left branch of our decision tree, and this is going to be the decision not to include nums of I. So basically we're skipping nums of I. So how am I going to do that? I'm going to take the subset and just pop the element that we just appended. And then I'm going to recursively run depth first search. I'm basically going to do the same thing. So these two function calls, while they look the exact same, they're going to behave slightly differently because for this recursive call, it's going to have a different subset given to it. And this recursive call is going to have an empty subset given to it. So now the only thing left for us to do is call our function. Of course, we're going to pass an index 0, that's the first value, and then we can return our result. So as you can see, it is an efficient solution. Luckily for us, the order that we have our subsets in the result doesn't matter. So for example, if we had an empty subset and we had 1, that's the same as if we returned 1 and the empty subset, right? Like the order that we put the subsets in doesn't actually matter. But again, I hope this was helpful. If you enjoyed, please like and subscribe. It supports
Is it just me, or does he suck at explaining? I mean, he's pretty good at most of the time, but like, what was that, man? Who's with me? Alright, let's see. Let's see how other people explain it. Here, look at this. This looks more intuitive. Result is blank. Backtrack. Start and the path. Result list is empty. First append the path, and for I in start to the length of nums, backtrack, 1 plus I do not get it. Wait. Let me go get a pen, you guys. Oh, I don't need to get a pen. My backpack is right here. Alright, let's write this down. Alright, so result so result equals, and then we call backtrack with index 0, path is empty. So we append path, which is just empty. So result now has the empty set. And then we do for I in range, start to end. So 0, 2, and then 4, 0, 2, 3, we will backtrack I plus 1, so 1, path plus nums at I, so nums at 0, nums is 0 is 1. So that would be this and 1, which appends oh, so this actually is just 1. So you add 1, so append 1. So this becomes 1. And then for 1, 2, 3, we will backtrack 2, and then plus 1, which is 2. 2, and then we have 1, 2 now. Right? 1, 2. Backtrack 1, 2, we'll append 1, 2. So this is 1, 2. And then 4, 2, 2, 3. So this was the last call. 2 to 3. We'll backtrack 3. 1, 2, 3, which appends 1, 2, 3. So now we have 1, 2, 3 up here. Okay. And then the for loop doesn't enter. The 3, 1, 2, 3, and so the present start 3 and path 1, 2, 3 at the current path. So 1, 1, 2, 1, 2, 3. I agree. Since 3, we can return this from the recursive call. To return from the recursive call, we start 2. Why are you removing? Oh, so that was just for that. Because now we go 0 to 3. So here we go. 4 0 to 3. This was last. So this is 1 for 1 to 3. So now it's for 1 to 3. Two plus 1, so it's BT 3 half plus nums at I. And then this is 1, 3. One, 3, append, 1, 3. So we got 1, 3, then 4, 2 to 3. And you don't enter this. 4, 3, 2, 3. So then this is fine, this is fine. So you did your, oh wait, that was for, okay, then from 0. 0, it's 1. So BT2, 2, so we append 2, 2, 4, 2, 2, 3, so it's BT 3, 2, 3, append 2, 3, okay, 2, 3, and then this would be 4, 3, 2, 3. Then we go to the very top, so it would be BT. This one is 2. Okay, append. So then from 0, so that was 1. And 2, so it's BT 2 plus 1 is 3. Whatever is at 2 is happens to be 3. So append 3. So now we do 3. And then this goes 4, 3 to 3, which doesn't enter. So we got 1, 2, 3, 4, 5, 6, 7, 8. So that's all though. So that's completely common. Here, I am completely unfamiliar with backtracking. I am trying to LeetCode some sense, but none of the ways I have studied feel intuitive. Please explain how I can think about these problems to come up with the solution myself naturally. Yeah, because this is really complicated. And everybody else it. Look at what happens in the first element. 1. Do I take 1? Do I not take 1? Mm-hmm. Honestly, don't get it. But I'll code it up and call it a day, I guess. Where are we at? 52 minutes. So the index of which one we're taking, and whatever the current is. And so cur is our ans is blank. And then we'll do backtracking 0 empty. If the length of cur, oh wait, no, if I is equal to length of nums, return, actually no, you append it, right? Otherwise, you either take it, which is I plus 1, and then cur. What? Cur dot append. No, this is I. Cur dot pop. No. Oh, it's cur dot, what is it? Append. This makes no sense. Okay, I gotta learn about this tomorrow, guys. Beats 100%. Wow. This is a red. This is like the reddest of reds. What is this? Subsets. $8.13. We're making this red for sure. It's even worse than a word search. Alright. Well, definitely calling it a day after that one. Alright, though. Yeah, sorry again for it being so short, you guys. But like I said, I got a lot of stuff going on, which I know isn't a great excuse. Honestly, I should make more time, but tomorrow I'm gonna be doing a lot of packing and gotta finish up my paper, and submit it, and I also got to take an OA, I'm pretty sure, for IBM, so wish me luck. But yeah, other than that, I guess I will see you guys hopefully tomorrow. Alright, see ya.